Thank you all for your interest in all things here at Turbo Rock, and in particular some of the work we've been doing on the torch igniter. The torch igniter, as you know, is just an element of the turbo rocket engine system, but I thought you all might find it interesting how we actually compute the performance of the igniter system, and in particular how we determine and establish the mixture ratio for the system. And we want to run it at a mixture ratio that doesn't melt the components. So we typically run it at a very fuel-rich mixture ratio, where the mixture ratio is determined at the flow rate of the oxidizer divided by the flow rate of the fuel. And that number is the mixture ratio, and it depends, on the types of propellants, how hot the temperature is going to be and things like that. You get the hottest temperature in which rocket engines run at is between about a mixture ratio of around 6 to 8. That's what's called the stoichiometric mixture ratio, and in that case, all of the hydrogens get paired with all of the oxygens to form the deadly dihydrogen monoxide, or water, steam, and that's the main constituent. But we don't want to run at that temperature because it'll melt our parts. So we run at a far more fuel-rich mixture ratio, and we run down around a mixture ratio of about 1, or even a little under that. So a lot more fuel than oxygen, and so it runs a lot cooler, but still hot enough to make a flame and ignite stuff. Plus, it has a lot of excited hydrogens that are good for igniting hydrocarbon type fuels. Anyway, so in our igniter here, the way we establish that mixture ratio is we use a series of choked orifices, these little guys here. And in this particular case, it's actually a double choked orifice, which means that we have choked orifices to control the fuel flow rate, but we also have a choked orifice at the throat. And so the way this works is when we introduce an upstream pressure to the fuel and then to the oxidizer, with that pressure drop across the orifice, we get what's called choke flow, which means that the flow at the tiniest size of the passage there, which is called the throat, is choked. This actually goes, it achieves sonic velocity. It's Mach 1 at the throat. And then that is actually true for all of these throats, this one, and it's also true for this one down here, and it's sort of what makes it sort of a double choke condition. Now, to get a choked condition, the pressure ratio across the orifice has to be greater than what's called the critical pressure ratio, and this is determined basically by the gas property known as gamma, which is the ratio of specific heats. And so gamma, sometimes abbreviated as K also, is what determines the choking pressure ratio for each of these orifices. And so we can actually establish a double choke condition as long as we're above the critical pressure ratio for both these orifices and also the main throat here, main throat exit orifice right there. And so the way we do that is we have flow rates through each of these orifice sizes, and we can, given a particular supply pressure, then and the orifice here, then we can simultaneously solve a set of equations to determine what the pressure settings we need to have upstream of the fuel and the oxidizer to achieve a given chamber pressure in here, which will choke this orifice as well. And I'm going to write that equation out. If you use Sutton rocket propulsion elements, which every would-be rocketeer should have and keep by your bedside and read regularly, you'll find that it goes through this pretty well. Now my copy is pretty wailed on, and I apologize for that. But basically, in the early part of the chapter, in one of the earlier chapters, where it goes to the basics, you can see that flow rate equation right here. So what it says is the flow rate through a choked orifice, and this is all gas, and that's compressible flow. The flow rate through that orifice is the throat area times the upstream pressure, the supply pressure, times gamma, or it's represented K in this case, multiplied by the square root of this quantity, which is 2 divided by gamma plus 1, and that quantity, 2 over gamma plus 1, is raised to the exponent of K plus 1 over K minus 1. So that goes under the radical, and then there's one more term, which is the square root of gamma RT. You all might recognize that square root of gamma RT is the speed of sound, which surely it is. So gamma, or K. R is the ideal gas constant. It's just, it's the gas constant for that particular propellant or fluid, which is the ideal gas constant divided by the molecular weight of the gas, multiplied by the temperature of the gas. So what we do is that equation applies for each of our three orifices. It's just that as long as the critical pressure ratio, as long as we're above the critical pressure ratio for each of the orifices, then we will have choke flow in these and also in the main flow. And so by setting the proper pressures for given orifices that we have in the fuel and oxidizer orifices, as well as the main chamber orifice, we can simultaneously solve those three sets of flow rates to obtain a solution that will choke everything and give us the correct mixture ratio. So I use a tool called TK Solver to solve these types of equations. TK Solver has been around a long time. It's just kind of a very nice little tool. You can buy it from UTS Systems. I think it runs about $200 or $300 these days. But anyway, it's really, if you haven't used it, it's a great little tool. It's kind of like MathCAD or Mathematica if you've used those kind of systems. But the way it works is you just type in the equations in standard kind of equational format here, and then it automatically knows what the variables are, and then we'll print those out. So basically, if you have n equations, it will solve for n unknowns. So it's up to you to put those equations in correctly and to have the right number of equations and the right number of unknowns. But in general, it will solve that set of equations. So for our purposes here, you can see some of the equations that we have. So the first one is right here. It's the mass flow rate equation for the oxidizer, and it's the same as this guy over here. So the mass flow rate of the oxidizer is equal to the area times the supply pressure times the gamma of the oxygen, times the terms that we've shown here. So we have that equation, that's for the oxygen. And then we have the same for the fuel. These are the properties, the same for the fuel. And then we have a third one, which is the main chamber. So the sum of those two flows, mix, burn, get hot, and then that flow rate is what's going through the main chamber, or what's called GG, the kind of the gas generator here. And then we have some other terms just to help the calculations along. We have some just curve fits for the temperature, the gamma, and the molecular weight of the mixture ratio of hydrogen and oxygen is a function of, or these properties is a function of mixture ratio. It's just a lookup table that you can put in there. And so when we load those values in, and then we load the all the knowns in, so we have an orifice size, and we have a supply pressure for the oxygen, and then we have the same for the fuel, an orifice and a supply pressure for the fuel side. Then we can hit the go button, and it will compute the mixture ratio that we'll get from those supply pressures at those orifices, and with an orifice at the gas generator. So these are all values from this little system here. So the fuel orifice is 0.038, and the oxidizer orifice is 0.026, and then the main orifice is let's see what it is. It's 0.109, or 10. They're 100 mils, 0.109 inches. So that's the main orifice. Anyway, so you put those values in, hit the solve button, and it tells you what the resultant mixture ratio is going to be. So in this case, it's 1.85, a little on the toasty side, getting up there, still quite fuel rich, it confirms. And if you have those flow rates going in the main chamber and it mixes and burns to make this gas temperature, then we'll have a pressure of down here. Oops, a little windowing kind of problem here. Of about 51 psig. That's the gas generator pressure. So not a super high pressure, but we don't have super high supply pressures either. They're only about 100 psig for the fuel and the oxidizer. And so that's how we compute that. Now, 51, we need to check to make sure that's above the critical pressure ratio. And so the critical pressure ratio in this case is less than 50 psig. It runs around 30 or so, and so we know that we're above that, so it'll choke. And the same with the fuel and oxidizer. The critical pressure choking pressure ratio on the fuel side is about 97, so we're above that, and on the fuel it's about 97.6. So we're above that. So we're all good. So anyway, so that's how that's done. And then these orifices, that gives us, for a given orifice, then we know that we need to supply a given supply pressure. So we'll stick that guy in there, and then same with the fuel, or the oxidizer, excuse me, and a little orifice there. Kind of see that little hole there, I believe. And that kind of goes down in there. And then on the main chamber, we have an orifice there, and it's just a modified A-N fitting with a B-nut, and so we just drop that down in there, and then screw that on. Kind of hard to do it here one-handed, but give it a go here, and yeah. So there you go. There's that orifice there, and then there's the orifices on the upstream side, and we use unions to thread down in these respective holes to cinch those respective fuel and oxidizer orifices down in there to keep them secure. So there you have it. And then when the spark plug goes here, so that's how that's done. So I hope you found that interesting. So when you're calculating the performance of a double choked orifice, it's math. So again, thank you for your interest in this, and I hope you'll continue to like and subscribe. It really helps out our channel here, and gets us to a point where we can develop technologies that you might find interesting and even useful if you're developing your own systems. Again, I wanted to reiterate that the torch igniter is just a way that we get the turbo rocket engine going. It's just a way to do that. It's not the only way or even the best way. But it is a way that can be done. And in a working turbo rocket engine, the igniter system would be kind of baked into the engine itself. But we're trying to just kind of flesh out the system and get it going so that we can establish working prototypes and also understand the numerical modeling so that our predictive codes and methodologies are suitable and will work. And of course, if you want to find out more about the design of turbo rocket engines, there's a book on the subject, and you can buy that book off of Amazon and read that fella, and you'll be a world expert by the time you get through reading and working the example problems in this book, because that's not because it's so hard, but because there's just so few people working on it. Anyway, so I hope you found that interesting, and I'll look forward to seeing you on the next video. And like and subscribe again, and thank you for your interest and support.